Hello everyone, my name is Romo Falcon and today I will show you the work titled An Actuator Fall Accommodation Sliding Mode Control Approach for Trajectory Tracking in Quad-Rotors. This work was developed by Héctor Ríos, Alejandro Zul and me, all being part of Tecnológico Nacional de México Campus La Laguna. This is the structure of my presentation and I will start briefly with a motivation of why we focus on this problem and then defining the problem statement. Nowadays, the use of quadrotors in industrial, civil, and military applications is gaining popularity due to their low cost, simplicity, as well as its capability to perform vertical landings and takeoffs. Thus, the design of robust controls emerged as an interesting research area. However, these techniques are effective when the system works under nominal conditions. In the presence of actuator faults, the control commands could not satisfy the required performance level. In this video, a quadrotor in a civil event that after the occurrence of a rotor fault, the quadrotor collide near to a person. This is the reason why the design of fault-tolerant controllers is required in this kind of vehicles in order to avoid dangerous situations. For this, let us introduce the dynamic model of the quadrotor that is given in the following set of equations, where he represents the position and eta represents the quadrotor attitude. We are considering external disturbances, inertial and drag coefficients, but one of the most important features of this system is that it is an underactuated system, having more degrees of freedom than control signals. The relation that exists between the control inputs and the thrust generated by each rotor is given by the following expression. In this work, multiple actuator faults given by loss of efficiency in each thrust are considered, and these are modeled in the following way, where the common thrust is affected by a fault factor given by gamma, or in other words, the thrust minus the fault. This fault factor can take two different values. A value equal to 0 means that the rotor is free of faults, or in nominal conditions, and a value between 0 and 1 means a loss of effectiveness fault, or LOE fault, in each rotor. So the problem statement is to achieve the trajectory tracking task for a quadrotor under the effect of LOE faults in multiple actuators, under the effects of external disturbances, and only by means of the measurable position and angles. There are several works in the literature related with the fault tolerant control on quadrotors, like the ones that are shown in this slide. However, in some of these works, the faults are considered as disturbances, and the authors deals with this problem with robust strategies. In some of them, do not consider external disturbances, and if they consider them, these affect the fault diagnosis. In some of these works, the authors only deal with the attitude subsystem, which is not a relevant problem in the trajectory tracking task, and all of them do not distinguish between faults and disturbances. In this sense, the main contributions of this work is given by the design of a fall accommodation controller that is proposed for a quadrotor in order to identify the magnitude of the faults, to achieve the trajectory tracking task in presence of multiple LOE faults and external disturbances, and in order to increase the fault tolerance of nominal controllers. In this section, I will show you the fault tolerant control design. In this figure, a schematic diagram of the proposed strategy is shown, where in blue we have the baseline robust nominal controller and in red the active fault accommodation controller. Such a fault accommodation is composed by three sections mainly. Firstly, by a finite-time sliding mode observer, which identifies both external disturbances and faults. Followed by a fault identification module, which identifies the magnitude of each fault. And finally, by the fault accommodation module that compensates the fault effect in the command control signal. For this strategy, we only consider the following states. The reason for this state space is due to the fact that the faults directly affect the control signals that are present in the dynamics of G1 and G2. Such dynamics are given in 1, where the faults are in green, the control inputs in blue, and the external disturbances in red. Before proceeding with the controller design, the following assumption is introduced, where we assume that the disturbances and faults are uniformly bounded and Lipschitz. Note that the total uncertainty affecting the previous system is given by delta, composed by both disturbances and faults, and due to assumption 1 is also bounded and Lipschitz. As I mentioned, a finite-time sliding mode observer is designed to identify both faults and some disturbances. Such an observer is given in 2, which is a copy of what is known about the system, and is based on the output error and the nonlinear output injections as follows, that use this notation. As a result, Theorem 1 is introduced based in Levant 2003, where using the previous observer and applying the dynamics of Chi1 and Chi2, and if we suppose that assumption 1 holds and the observer gains are selected as follows, then the position and velocity estimation error are uniformly finite time stable. Moreover, according to Theorem 1, the observer estimates the positions, velocities, and also identifies the unknown inputs given by the external disturbances and faults in finite time. The next step is the design of the fault identification model, which identifies the magnitude of each fault. For this, due to assumption 1 and the estimation properties of the observer, upper and lower bounds of each disturbance can be obtained through free false experimental tests, where are used in the following sigma variables. These functions provide an approximation of the disturbances, taking into account the sign and magnitude of each residual signal. Based on these variables, the following proposition is introduced, where the fault identification is given by this expression, which is composed by dynamic terms of the quadrotor, the partial identification of the external disturbances, and the residual signals provided by the observer. Once we have the fault identification, the following active fault accommodation control is proposed, which is given by 3, where the control inputs are composed by both nominal control signals and the fault identification, and as a result, the current thrust is given by the command thrust minus the fault identification error. Thus, using the measurable outputs of the quadrotor, residual signals are constructed by means of the finite time sliding mode observer. The fault identification model identifies the magnitude of each fault, and finally, the fault accommodation control compensates the effect of each fault in the command thrust. Such a command thrust is generated by our baseline robust-nominal controller. In this work, we consider the following structure for the baseline robust-nominal control, where the position control is defined by a PID control, while the attitude controller is defined by continuous twisting controllers. In order to deal with the underactuated nature of the system, a virtual control input is introduced in the position subsystem, and the following nonlinear decoupling terms are considered. If the fault accommodation control is applied, the control inputs take the following form, which are given by the nominal controllers and the fault identification injection. The nominal virtual control is assigned by a PID controller and some terms that are known of the dynamics, that is shown in 4, and the attitude control is given by continuous twisting controllers and some terms that are known of the dynamics given by 5. Then the following theorem is introduced. If the previous controllers, considering the fault accommodation technique, be applied on the quadrotor, and suppose that assumption 1 holds, then the position error dynamics is input to state stable with respect to some disturbance terms and the fault identification error, and the attitude error dynamics is uniformly finite time stable. In order to show the effectiveness of the proposed strategy, experimental results are shown. Such a strategy was implemented in the Q-Ball-2 Quad-Rotor and the OptiTrack camera system, both given by Quanser, and for the external disturbances we considered the wind gust generated by an industrial fan. For this, consider the Q-Ball-2 parameters given by Quanser and consider an helicoil desired trajectory. Also consider the 20% of loss of effectiveness in the first and third rotor after 50 and 45 seconds respectively, while rotors 2 and 4 are free of faults. The tracking task in the translational coordinates is shown in this slide, where despite the loss of effectiveness faults, both controllers make the quadrotor track the desired trajectory. However, adding the fault allocation scheme in the baseline robust nominal controller, the position tracking performance is improved. In these figures, the shaded light gray area depicts the time when the first fault is active, and the dark gray when both faults are active. In these figures, the desired trajectory is given by black, the fault accommodation control in red, and the baseline robust nominal controller in blue, which is given by the combination of PID controllers and the continuous twisting controllers. The behavior in the trajectory task of the yaw angle is similar, which is improved when the fault accommodation control is active. The fault identification of the first fault is shown in this slide, where the fault identification module partially estimates the magnitude of the fault, even in the presence of external disturbances, and a similar identification is obtained for the third fault. The thrust generated by each rotor is shown in this slide, where the control effort in the fault accommodation control is more aggressive, being a drawback in the proposed scheme. In order to better illustrate the performance of the controllers, the average value of the root mean square of each position error signal and the yaw angle error are computed, and they are illustrated in this slide. Note that using the same nominal controller, same gains, and under the effect of the same faults, the fault accommodation control improves the performance in each coordinate. As conclusions, a fault accommodation control is designed for a quadrotor under loss of efficiency faults in multiple actuators, under external disturbances, and achieving a trajectory tracking task. Such a strategy ensures the finite time convergence to zero of the attitude error and exponential convergence to the neighborhood of zero of the position error. This strategy is independent of the control loop. That means that this strategy can be applied in nominal controllers in order to increase their fault tolerance. Thanks for your time.